This is Math 31, where we are looking at calculus and pre-calculus at the moment as we explore limits. We are in lesson 1.3, where we look at one-sided limits. In the previous video, we looked at this fairly complex definition of a limit, and today we're going to get more into the idea of one-side limits and continuity. So we start with, well, a couple of statements that aren't actually definitions. It's more a matter of notation. A left-hand limit is the limit as x approaches a from the left. So that makes perfect sense. And notice here in the notation, this little negative sign in that exponent. So when we have that negative sign kind of looking like it's in the exponent for the a, it says we're approaching a from the left side. And you can guess what a right-hand limit is going to look like. Dun, dun, dun. If we're approaching a from the right-hand side, then we have this little plus in the exponent, so we're coming from the positive side towards a. So that's how we show in notation that we're finding a left or right-hand limit. We say that a limit exists if the left-hand limit is equal to the right-hand limit. We've talked about that previously. We're just making it a little bit more formal with this notation. We also talked about continuity previously, but we really didn't get very far into it. This lesson will help us understand it even better. We would say a function is continuous at the point where x is equal to a, if and only if. I'll explain that in a moment, but for now, let's just say if the left-hand limit is equal to the right-hand limit and is also equal to the value of the function. So, continuous if the limit exists and the value of the limit is the value of the function. That's how we described it previously. Now, taking a sidestep to a completely different definition. In grade 11, you looked at piecewise functions, particularly related to absolute value. A function that's described by different formulas or different equations for different parts of the domain is called a piecewise function. Today, we're going to look at a few different piecewise functions. But first, let's look at left and right hand limits graphically. For question number 1, I'm looking for the limit of the function as x approaches -6 from the left side. So note that we had that little negative sign in the exponent. So what I'm doing is, let's see, 1, 2, 3, 4, 5, 6. I'm approaching -6 from the left side. And as I come along my function, I look to see what's the y value approaching. Well, it looks like it's getting closer and closer to this value of -2. So we'd say this left-hand limit is equal to -2. Question number 2 is looking for the right-hand limit. So as I come from the right-hand side and I'm approaching this value of -6, what happens to my function? Well, my function decreases, gets closer and closer to this same value of -2. Well, up above, we said a limit exists if the left-hand limit is equal to the right-hand limit. So for question 3, notice there's no little superscript here. We're just saying what is the limit of the function as x approaches -6. And because left and right-hand limits were the same, we say the value of the limit is equal to 2. Let's come over to the right side here as we look at number 4. The limit as x approaches 2. Well, I should have switched the order here. I can't answer number 4 until I answer number 5 and 6. So let's look at number 5 first. X is approaching 2 from the left side. So I'm approaching in this direction. What's happening? Well, my y values are going down here, and it just looks like it's approaching -infinity. Now, if the graph goes down forever, we'd say that this limit does not exist. So I'll just write DNE for does not exist. So the left-hand limit does not exist, but often we want to know what's happening. And so I'm going to say that it is approaching it's approaching negative infinity. Here in number 6, as I look at a right-hand limit, as I approach from the right side of 2, I see my graph is going up here. So here it's approaching positive infinity. So again, I would say this right-hand limit does not exist, but I can say it is approaching positive infinity. Well, my left and right-hand limits don't exist, which means that the limit of my function as x approaches 2 also does not exist. And since left and right are approaching different infinities, I wouldn't even say it's approaching an infinity because it's different on either side. On to number 7. As x approaches negative 1 from the left, what's happening? Well, here as we approach negative 1 from the left, our function value is staying constant here at negative 1. So this limit is negative 1. As we approach an x value of negative 1 from the right side, what's my y value approaching? Well, it comes here, it's at negative 4, and it comes up a little bit above negative 2, but then comes back down and is approaching negative 2. So we'd say the right-hand limit is equal to negative 2. Since the left and right-hand limits are different, we say the limit of the function as x approaches negative 1 does not exist because they're approaching different values. So notice if left and right-hand limits are approaching different values, we say the limit doesn't exist. Or if they're approaching an infinite or infinity, we would say that the limit doesn't exist as well. Well, why don't you try a few? So take a look at these next 6 questions and see what you come up with for these limits. Pause the video and restart it once you've answered up to 15. Well, let's look at number 10. As x approaches negative 4 from the left side, we'll scroll up and have a look here. Negative 4 is here. From the left, our function is coming up here, and we're approaching a positive 1. From the right, we're constant here, and we're approaching a negative 1. Left and right-hand limits are different, so our function does not have a limit at that point. Left-hand limit, we said, was positive 1. Right-hand limit was negative 1. So we say this limit does not exist. How about at positive 5? Well, here as we look at positive 5, from our left side, our graph is going up towards infinity. From our right side, it's approaching infinity. So it's approaching the same value in a sense. But remember, infinity isn't actually a number. Infinity is just further. So we would say that the left-hand limit does not exist, but is approaching positive infinity. The right-hand limit does not exist, but it's approaching positive infinity. So the limit at that point also does not exist, but we can say it is approaching positive infinity. That's the graphical exploration of left and right-hand limits. Now let's come back to discontinuities, and we'll look at them a little bit differently. So let me first come back here to our definition, where we said a function is continuous, f of x, at this point, if and only if. Oh yeah, I said I'd come back to that. If and only if means it's continuous if these two equations are true, or if this whole set of statements is true, then we can conclude it's continuous. So if and only if means continuous implies this is true, and given this information, that implies the function is continuous. So it goes in both directions. If this, then that, or if that, then this. That's what if and only if means. Here's we look at it slightly differently. We'd say f of x is continuous at a number c if the value of the limit is equal to the value of the function. That's how we looked at it in lesson 1.2. Here's another way we can look at it. Three things are required for the function to be continuous at the point c. First of all, the function must be defined. If the function is not defined at that value, oh, I used a instead of c. I need to fix these notes. Let's come up here and we'll just change this to an a because all these other statements will have a's in them. Should probably just change all of these to a's too. As x approaches a equals f of a. There we go. So function has to be defined for this value of x. In other words, a is an element of the domain. And the limit must exist. So left and right hand limits must equal each other. And the third condition is that the value of the limit is equal to the value of the function. If a function is not continuous, then we say that the function is discontinuous at that point c. Again, why don't I change these all to a's so I'm a little more consistent. One of these days I will learn. And we can say that the function has a discontinuity at the point c. And we talked about points of discontinuity in Math 30-1. But here we're saying a gap is also a discontinuity. It's not just a hole in the graph, but if there's actually a gap as well, that would be considered a discontinuity. So now we're going to look at this similar or the same piecewise function, really, graphically, and we want to look at, is the function continuous or discontinuous at these different values? To do these questions, I'm going to look at these three conditions up here. Is the function defined? Does the limit exist? Is the value of the limit equal to the value of the function? So first of all, when we look at x equaling -6, we see that when my x value is -6, yep, my function is defined, and my function is equal to -1. Does the limit exist? Yeah, we said the limit exists because left and right hand limits were the same thing. Left and right hand limits were equal to -2. But the function is discontinuous because f of -6, which is equal to -1, is not equal to the value of the limit, which was -2. So they were not equal, so we'd say the function is discontinuous where x is equal to -6. Visually makes sense, but I wanted you to think about these three characteristics as well. As x approaches -4. Well, as we look at this graph, we can see, well, there's a gap. It'll be discontinuous. But let's look at these three conditions. Is the function defined? Yep. The value of the function when x is -4 is equal to +1. So there it's equal to 1. Does the limit exist? Nope. Left and right hand limits are different. The left hand limit is a 1. The right hand limit is a -1. So the limit doesn't exist, so we don't even have to look at that third condition. We'd say the function is discontinuous, where x is -4. Why don't you think about question 18 at -1? Will the function be continuous or discontinuous? Well, visually, just looking, we can see that there's this gap, which means it'll be discontinuous. But again, as I look at my conditions, the function is defined. F of -1 is equal to 0. But my left and right hand limits are different. My left hand limit is a -1. My right hand limit is a -2. They're not equal, which means the limit doesn't exist, and so the function is discontinuous at x equal to -1. Why don't you pause the video and take a look at question number 19 and question number 20, when our x value is 5 or when it's equal to 6. Well, f of 2 is undefined. Again, as we look at our graph, we see that we had a vertical asymptote there, so the function is not defined there, which means it's discontinuous. As x approaches 6, well, let's have a look here. As we approach from the left side, looks like we're approaching this y value of 1. From the right side, also the value of 1. That is the value of the function, and so our graph is continuous when x is 6. f of 6 exists, left-hand limit is equal to the right-hand limit, and the value of the limit and the value of the function are equal to each other. They were both equal to 1, which means our function is continuous where x is equal to 6. Now, graphically, it's fairly easy. Sometimes it's a little bit more challenging once we look at equations. So here we have a piecewise function. And as I look at the two parts of the definition for this function, I have a polynomial and a polynomial. Polynomials are defined for all real numbers. So each of these two pieces will be continuous everywhere. The only point that we need to wonder about is where the definition changes. Is there going to be a gap, or will these two functions come up and touch each other, or come infinitely close, because here we're less than -1, here we're greater than or equal to -1. So here's the first step. I need to look at what's the left-hand limit. Well, my left-hand limit, I'm looking as x approaches -1 from the left side. Since I'm coming from the left side, it means that my x values are less than -1. So I need to use this part of the definition as I do my left-hand limit. So there we go. I'm using this part of the definition. And when we're finding a limit, as we saw in our previous lesson, if we can just plug in a number for x, that's what we want to do. And so I can just plug in the -1, evaluate, and I get my left-hand limit is equal to 3. Next, we'll look at the right-hand limit. So here, as I'm doing the limit, as x approaches -1 from the right-hand side, that little plus in the exponent there, I'm looking for values of x that are greater than -1. So I'm using this x squared plus 2 definition for the function as I do my right-hand limit. And again, I can just plug in the -1 in order to evaluate. Since my left-hand limit is equal to my right-hand limit, they both equal 3, that is the limit of the function. So in this case, for this question, we were just asked about what the limit is. We weren't asked about continuity, but we'll talk about it when we look at the graph. So we're asked to sketch the function. So I have this linear function, 3x plus 6, up to an x value of -1, coming infinitely close but not reaching it because x is less than but not equal to -1. On the right side, I have this parabola, x squared plus 2, so my vertex will be at 2. And when I sketch that, here's what I get. The left and right-hand limits are approaching the same value, and if we were asked about continuity, we would say this function is continuous everywhere, because left and right-hand limits, as x approaches -1, are both equal to 3, and the value of the function is also equal to 3 when x is -1. So the limit exists, it's equal to 3, and the function is continuous as x approaches, or at the point where x is -1. Why don't you try question 22? Pause the video and restart once you've worked through the question. Well, here you see my work. I did a left-hand limit, and a left-hand limit I had to look where x is less than 5. So I used that quadratic expression, substituted the 5 in, and got the limit from the left is 7. From the right, I get 10 times x. If x is 5, I'm going to get the square root of 50, which is close to 7, but it's a little bit bigger. Left and right hand limits are not equal, so the limit as x approaches 5 of this g of x function does not exist. Now let's look at continuity. For question number 23, f of x, our function, is equal to the absolute value of x. Well, from what you know about absolute value functions, you can probably picture it in your mind and you'd say, well, yeah, it's continuous everywhere. But notice in the box above, as with proofs, the goal here is not simply to convince yourself, but to clearly communicate a well-reasoned answer for others to understand. So, is this function continuous everywhere? Well, first, what helps us in answering a question like this is to think about the piecewise definition of absolute value. That piecewise definition says the absolute value of x is equal to x if x is greater than or equal to 0. So absolute value of 7, that's greater than or equal to 0, that's just equal to 7. If x is less than 0, then I have to take the negative of the number. So for example, if x was negative 7, well, negative 7 is less than 0, so I take the negative of negative 7, which gives me positive 7. So that's the piecewise definition of absolute value. Since y equals negative x and y equals x are polynomials, they're continuous everywhere. So again, the only point that we need to be concerned about is where x equals 0. That's where we need to test for continuity. So let's look at those three questions again. Does the function exist? It exists. F of 0 is the absolute value of 0, which equals 0. Check. Second question, does the limit exist? Ooh, well, there's some work. I did the left-hand limit. Notice a little negative in the exponent. And I'm replacing the absolute value of x with that left side definition, which is negative x. When I plug in the 0, I get 0. Same thing for the right-hand limit. Here I substituted in the x. That's the right-hand definition when x is greater than or equal to 0. Both of them are equal to 0. Value of the function is 0. Value of the limit is 0. Therefore, I can conclude that this function, f of x equal absolute value of x, is continuous everywhere. Number 24. Here we have a more complex piecewise function. Again, for this first piece, it's polynomial, continuous everywhere. Second one, polynomial, continuous everywhere. So I just need to check when x is equal to negative 1. Here, this radical function is only defined when x is greater than or equal to 1, but it's continuous wherever x is greater than or equal to 1. So this part of the definition is also good. Again, I'll just need to test when x is equal to 1, will our function, this piecewise function, will it be continuous or not? So let's start by looking where x is equal to negative 1. Is the function defined? Well, as I look up here at my definitions of the function in piecewise form, I can see that here, x is equal to negative 1. So the function is defined, and I can determine a value of the function using that top polynomial part of the piecewise function. Then I look at the limit. So I want the left-hand limit and the right-hand limit as x approaches negative 1, and I see both of those are approaching 0 as well, which means value of the function is 0, value of the limit is 0, so our function is continuous because the value of the function is equal to the left-hand limit, which is equal to the right-hand limit. How about when x is equal to positive 1? What's happening? Again, I look to see, is the function defined? So before I scroll down too far, here we can see that when x can equal 1, I will use this radical piece of our piecewise function. So the function is defined, and we can evaluate to find f of 1 is equal to negative 1. There's the first step. Second step, we want to know what is the value of the limit. So I need to do a left-hand and a right-hand limit. And notice here, as I do my left-hand limit, I'm getting a value of negative 2. So even at this point, I can see that my left-hand limit is not going to equal the value of the function, so I could just stop there. My function is discontinuous at x equal 1 because the value of the function is not equal to the left-hand limit. And so I don't have to continue with the rest of the work as long as I've shown this much. If I wanted to find a right-hand limit, I would see it is equal to negative 1. It is equal to the value of the function, but left and right-hand limits are not equal to each other. Well, the next page gives you some check your understanding questions. Oh, but up here I have a grid. I'm guessing that's telling me that we want to have a look at this graph. What does it look like? Well, let me do a rough sketch here, and rough it will be because I'm using the tablet here. So as I look here for this first part of the function, I'll do this part in red. X squared plus 2x plus 1. That's factorable to an x plus 1 squared. And math 30-1 helps me out here. I have where x is equal to negative 1 at this point. My function is defined for that part, so I have a solid dot here. This would be a parabola that opens up. I have a multiplicity of 1. And so I only do these values going in this direction. So I have this parabola that's curving up. Oh man, that's bad. Well, you can draw better than that. But that's as good as I'm going to get for that piece. And then let's have a look at this middle part. It's a line. Slope is negative 1, and my y-intercept is negative 1. So there's my y-intercept. This is how my function is defined between negative 1 and positive 1. So I have an open circle here, and I'll actually have an open circle here as well. But in between, we have a line connecting those points. So let me choose the color, and here's my line connecting those two endpoints. In other words, both are less than, and so I have the open circles there. And then finally, we have the radical function. Let me think through this graph with you because you need to be able to do this without a calculator, right? So I'll go blue for this part. And let me start by thinking about what does y equal the square root of x look like? And then I'll do transformations. So y equals the square root of x has a vertex here, and then it's half a sideways parabola, so it goes through those points. So it's going to curve up and then go to the right like this. Okay, that's better than that first red graph. On paper, you can do better than this. So yes, I'm expecting better graphs than I have sketched here. But now if I have this x minus 1, that translates this graph to the right by 1 unit. And then this minus 1 outside the radical tells us this whole thing is translated down by 1 unit. And the equal sign tells me I should have a solid dot here. So my piecewise function is defined everywhere. The domain is all real numbers, but this gap, good grief, gap in the graph just re-emphasizes the fact of what we discovered here, that our function was discontinuous where x was equal to positive 1. All right, time for some check your understanding questions. Pause the video at this point, work through these questions, and then once you're done them, you can restart the video. Well, the first question when we're looking for continuity is the function defined everywhere? Well, we can see that we have a rational function. It's not defined when x is positive or negative 2, so our function is discontinuous when x is positive 2 and negative 2 because it's undefined for those values. And as we've learned before, rational functions are continuous everywhere else. There's number 25. Number 26. So first time, so all three of these are polynomials, so continuous everywhere. I'm just looking at the joints, really, where these two pieces of the function might come together. So we check when x is negative 1. I look at the left-hand limit. I look at the right-hand limit. I look at the value of the function. All three of those are equal. Therefore, it's continuous where x is equal to negative 1. Notice that in that question, I came back and I used this definition of continuity here, where we said it's continuous if and only if the left-hand limit equals the right-hand limit equals the value of the function. Then as we look at the next possible gap in the graph where x is positive 1, we look at the left-hand limit, we look at the right-hand limit, they are different. Limit doesn't exist, so without going any further, we know that our function is discontinuous where x is equal to positive 1. And what do we get for a graph here? We get this for what our graph would look like. On to number 27 and the piecewise function. Well, this one's a little bit different. We haven't seen one like this in our examples yet, where here we have the function defined to the left side of 3 and to the right side of 3, and then we have a unique definition for the function at that point where x is equal to 3. So as I look at the left-hand limit as x approaches 3 from the left, I'm using this top function, so that's why I have the rational function here. I can find a common factor to reduce, and then I can substitute in, and I get 6 for my left-hand limit. My right-hand limit, x is greater than 3, so now I'm using this piece of that piecewise function. I plug in the 3, and again it evaluates to equal 6. So the limit exists when x is equal to 3. But we see the value of the function is 9, not equal to the value of the limit. Therefore, this function is discontinuous at x equals 3 because the value of the limit is not equal to the value of the function. That finishes off this lesson. Whew, time to do some practice. Have fun.